All right, let's get started. So in this session, what we're going to do is we're going to look at some research frontiers. So this is somewhat different from what we've done so far in these 2 days, because so far we've looked at things that you could put into practice. And now we're going to look at things that probably are not ready to be put into practice, but that are at the frontier and maybe next couple of years will become ready. And it's good to get a sense for where things are headed, what's becoming possible that wasn't possible before. Now, when you think about research, maybe the first thing you think is papers, because when you do research, you write up your results in paper, and so maybe the easiest way to keep up with research is to just read the papers. Now, AI has become so popular, so many people working in it, that you actually cannot really keep up with the papers coming out. So there's more than 100 papers every day coming out on arXiv. And so that's not going to be the solution, and we'll look at some solutions later how to keep up. But for now, what I want to do is give you an overview of what are the main directions where there's just a lot of activity that's very exciting and where things might become feasible in the next few years to start putting into practice. So here's a non-exhaustive list of directions that I think are really exciting and where there's a lot of interesting research yet to be done, but also already some great signs of life that progress is being made. Now, we can't cover all of this in the session we have, so I'm going to cover what's in the first column, but what's in the second column is just as important, just as interesting. It's just a matter of time. So as outlined for the session, what I want to do is first sample research directions, the ones listed on that previous slide, then zoom out and get a sense of the overall research theme that cuts across all of them. And then actually I want to give a little bit of perspective on the gap that I'm seeing between research and real world, especially in robotics. So I'm trying to put robotics research results into action in the real world. We see all these demos, very cool demos, but how come we don't see any robots yet? There's actually a big gap there. I want to highlight that a little bit, and also give some pointers on how to keep up with everything that's happening. Actually, one question I'm curious about is, I know from last night a couple of you are actually PhD students and are doing research. So who here is doing research right now? Wow, so about half of you. OK, that's pretty impressive. Among the ones doing research, how many are doing research that turns into writing papers? OK, most of you. OK, great. So yeah, maybe one of your papers will pop up somewhere here. We'll see. So let's start with few-shot learning. What's the starting point here? At a high level, supervised learning has had huge success. It works. And you can put it to work on your own problems. But the requirement is that you need a lot of labeled data. Now, let's contrast that with humans. There was a time in your life you'd never seen these. On the left, a hoverboard. On the right, a one-wheel plus. But after seeing just one of them, you would immediately know that this one is also a hoverboard. This one's also a one-wheel plus. This one is also a one-wheel plus. And this one's a hoverboard. So how come our deep neural nets need so many examples, yet humans, from one example, already know what the category is? Well, why can we do this? Maybe it's because we have a strong prior notion of what object categories are like. Because we've seen many other categories before, and by having seen members of a category, we start understanding how we can generalize from one member of the category to all other members of that category. So how can we do the same thing for our neural nets for machines? Well, the starting point will still be a lot of data. We're not going to get away from that. But the hope is going to be that we can get a lot of data ahead of time on other things. And then when time comes to solve the problem we want to solve now, we only need a small amount of data on the new problem. So quite a few approaches that try to tackle this problem. What I'm going to look at here with you is something called Model-Agnostic Meta-Learning. And I'll give you a lot of other references too, but this is the one we're going to dive into. The starting observation here is that, well, look at computer vision practice. What do people actually do? Well, if they have something new they need to solve and they don't have any data for it, well, they take something that's trained on ImageNet and then fine-tune it on the task they actually care about. It actually works really well, and it was shown soon after the AlexNet results. But you might have some questions about this. You might say, well, how does it generalize to maybe learning behaviors rather than learning something about images? Or how can we try to force it to succeed rather than just hope for the best? Because this really, kind of, you train on ImageNet and you hope it's going to work on something else with just some fine-tuning. It's not really a full end-to-end approach for success. It's more a hoping for success, and usually it seems to work. So how can we do this more end-to-end? So key idea behind Mammal is I want to do end-to-end learning of a parameter vector theta, which is the parameters of the neural network, that is a good initialization for fine-tuning for many tasks in the future. So at test time, we're going to be doing fine-tuning. What does that mean? There's going to be a parameter vector theta that we have ready in the neural network to go. But then we're going to have new data for the new problem. And what are we going to do? We're going to fine-tune. So we're going to take a gradient step against the loss on that new data. And then we'll have a fine-tuned parameter vector, which we'll call theta prime. If fine-tuning is successful, that would mean that theta prime is a good parameter for the new task. What that in turn would mean that theta itself was a good pre-trained parameter vector. And that's really what we're after, finding these good pre-trained parameter vectors theta so we can fine-tune quickly. So how do we do that? If you just pre-train on ImageNet and then fine-tune on your task, you're not really guaranteeing that. You're just hoping that that theta will work. But if you look at this, we're going to actually try to force this. So imagine we have many tasks. If we have many tasks, then we can actually check at training time when we try to find theta. We say for our many, many tasks indexed by I, for each task, we'll do an update, a gradient step, that's specific to that task I, get a new fine-tuned parameter vector, theta I prime, specific for task I, and then we'll look at the validation data and see how well that parameter vector, the fine-tuned one, does in the validation data. If it does well, that means the pre-trained parameter vector theta was good because it was ready to be fine-tuned onto task I. If that's true for all tasks I, then there's a good pre-trained parameter vector for many, many tasks. And then you might hope, if that's true at training time it's ready for every new training task, then at test time, it might also be ready for a new test task. And so the level of generalization you see normally is from training data to test data. Here, we're kind of lifting this and we're saying we're going to try to generalize from training tasks to test tasks, where the performance we get on training tasks is the ability to adapt in one gradient step to whatever is the task, and then we hope the same performance will happen at test time, where we adapt in one gradient step to the test task. Putting this in a different kind of figure, there is some high-dimensional parameter vector space where theta lives in. Then we want to meta-learn this parameter vector such that we can jump onto optimal parameter vectors for other tasks very quickly, which we call theta I star. And so pictorially, we have a space in which we're optimizing theta. We're not optimizing theta itself to solve any one of the training tasks, but we're trying to position it such that it's close to many solutions and close defined as, well, will a gradient step get us onto a solution? Because that's what we're going to use at training time, at test time. When we do an update, it's going to be a gradient step. So we want to be ready for, with one gradient step ideally, getting onto the solution. Of course, we're allowed to do more than one gradient step, but if it's ready to do it with one gradient step, that's ideal. OK, so what might this look like? Well, the standard data sets for evaluating this are the Omniglot data set and the mini-ImageNet data set. So here is the mini-ImageNet data set. We have meta-training on a set of classes. And so here what happens is each task at meta-training time is a 5-way classification task. It's a 5-way classification task into classifications that are different from the classifications that will appear at meta-test time. So meta-training has its own categories on which you learn to classify. But it's not about learning to classify into those specific categories. It's about learning a parameter vector theta that's ready with one gradient step to learn to classify any one of those 5 categories. Once we've done that, we go to meta-testing where new categories will appear. And we hope that, again, in one gradient step, it will adapt. How well does it work? Well, here are some numbers. So on Omniglot, which is a handwritten data set, so handwriting recognition. We have 1-shot and 5-shot here on the left. So 5-way classification. So at test time, you're given examples from 5 categories. Then in 1-shot, you're given 1 example of each of the 5 categories. In 5-shot, you're given 5 examples of each of the 5 categories. And you see that the mammal approach in green has actually very low error rate. For example, 5-shot has lower than roughly 0.1% error rate with just learning from 5 examples to categorize 5 new handwritten characters. So it's a very low amount of data compared to what we're used to in deep learning when learning something new. 20-way, of course, is harder, and you see that errors are a little higher, but still very low relative to the amount of data being used. Mini ImageNet, similarly there. ImageNet goes into 1,000 categories. Mini ImageNet has only 5-way here, so we have 5-way classification at test time. And so random would be 80% error rate. We see that we do much better than 80% error rate from just 1 example of each category, and about 35% error rate with 5 examples of each category. So if you want to read more on this, there's actually a lot of work going in this direction. There is a list of references here that are looking at, some of them are building on Mammal, which I just described. Some of them look at slightly different approaches like matching networks or prototypical networks, which learn embeddings and then do something like nearest neighbors in the embedding space. Actually, let me go to the next slide, which has even more references, but in a smaller font. So here you have, including the 2018-19 references at the bottom, a lot of work going in this direction beyond what's listed on this slide, but this might be a good starting point if you want to learn more. So the setting in which you would apply this is when you have new classification problems you'd like to solve in the future that are related to your old ones, and you want to be maximally ready by having trained on the old ones, not to just train on them, but train to be ready to learn something new in the future. So one place we actually apply these ideas is, Sergey applied is at Gradescope. Because at Gradescope, what do? We learn to categorize student work into, well, simplest version would be correct or wrong answer, but often the rubric is a lot more detailed, so we want to, for each answer that a student gives, decide which rubric items apply to categorize the quality of their work. And so here are some examples of essentially data types that we did meta-learning on to be able to adapt to new questions instructors come up with and answer students give to those very quickly, which empirically we found allows to save about 90% of your time on grading because you grade about 10% of the answers, and that's enough to get everything graded. Now, this has been so far classification. You can do the same thing for optimization. You can say, I don't like gradient descent, but I have optimization problems that are of a specific family that have a certain character to them. And so if they're all of the same character, then maybe I can learn a different optimization scheme that will work a little better than gradient descent because it understands the properties of the family of problems I'm trying to solve. And you can take advantage of that, build a prior from your past examples as to what the right updates are to do better on your future optimization problems. So a couple of references here. And you can also do this for generative models. So you can say, if I'm going to be required to generate, let's say, a new handwritten character, can I ahead of time train on many handwritten characters, not just to learn to generate them, but to learn to generate them from one example, such that in the future, when I'm given one example of a new character, I'm ready to also generate the new character. So maybe we'll pause here for questions.
How does Reptile compare with Mammal?
So that's a pretty detailed question. But essentially, in Mammal, we have this optimization over here. And essentially, if you look at the details of this optimization, Reptile makes a slight simplification. If you look at all the derivatives that pop up, it makes a slightly simpler version of what this will end up being. This will end up being requiring second-order derivatives. Reptile kind of avoids that, but gets something very close to what's in Mammal without needing second-order derivatives.
For Mammal, how do we know that there is such a theta, right? How do we know that there's a theta that should perform well in all tasks?
Yeah, that's a good question. So if you look at the tasks people consider, often they're very related tasks. And so people have a hunch that for these tasks, there might be one theta that can be shared across all of them. For example, all handwriting recognition or all images, ImageNet-like images. Haven't really seen it where the meta training is handwriting and the meta testing is ImageNet, because that's such a big mismatch between the data sets. So part of it is to have something where I would say your tasks are sufficiently related, but it's hard to know what that means, but people just have some intuition about, okay, what does it mean to be related? The data input looks somewhat similar in both tasks, and they might be sufficiently related. If there's no such thing, then you'll find at training time that this loss will remain high. So you'll find that, okay, no matter how long I train, this loss is just not going down because there is no theta that I can find that allows me to quickly fine-tune on any member of this family of tasks.
There's a question about training time for Mammal. So how does that compare to, say like just joint training on all the tasks?
Joint training on all tasks versus Mammal training, I don't have a precise answer to that because I haven't, when students were the ones running the experiments, but my hunch is that especially if you were to use the first order approximation, which is often used, it shouldn't be very different. If you use the full second order version, it might depend on how long it takes to get your second derivatives, if it's about equally fast or not.
Can you comment on the differences between active learning and meta-learning?
Yeah, sure. So active learning is about collecting, well, there's a few definitions, but the kind of standard, one of the standard definitions is in active learning, you have a large data set, and maybe not all your data has been labeled. And so you might say, okay, since not all my data has been labeled, I want to actively think about what data is more valuable to get labeled. And then get that data labeled and train again with that data added in the mix. So that means in practice, you would maybe train on your labeled data initially, and then you might start looking at, well, which other data points that I don't have labels for am I very uncertain about? For example, instead of training one network, you might train an ensemble of networks. And in your ensemble of networks, when it disagrees, that's something you're very uncertain about based on your training so far. And then those examples might be candidates for you to get labeled, and active training would kind of drive that process. So it's actually quite different from meta-learning, but there are, of course, some relationships in that. You are looking at a large amount of data, and you are not just doing straight-up supervised learning on it. OK, great. Well, great questions. So that's one research highlight. Second one I want to look at is reinforcement learning. Actually, a question on that, too. How many people here have implemented reinforcement learning before? Wow, that's amazing. OK. Even Josh. Many times. So how many of you have implemented the, well, you could have used reinforcement learning or implemented the algorithm underneath. How many of you have implemented one of the algorithms underneath? Oh, wow, a lot of you. I'm curious what you've implemented. Who has implemented, let's say, PPO? A few of you. Who has implemented Q-learning method? That seems very popular. Who's implemented an actor-critic method like soft actor-critic or something? OK, very interesting. Curious why Q-learning is so prevalently implemented. In what context did people implement Q-learning? Of the people who did Q-learning? Like, what was the context in which you did it? Class. I see. When it's part of a class. Got it. All right. So, well, maybe we'll make the other things also part of a class sometime soon. If you want to do, actually, if you want to do PPO as part of a class, we just released the homework on PPO in CS287 at Berkeley. We'll soon post it also on the public website. So if you want to do that, you'll have a chance very soon. If you don't see it right away, feel free to reach out to me. So what do we do in reinforcement learning? We have an agent, and the agent is supposed to interact with the world. And through interaction, learn how to collect high reward in the world. What does it mean to get high reward? Well, maybe if it's a video game, it could be achieving a high score in the game. Or maybe if you're a robot that's supposed to make meals, then it's making a high-quality meal would be high reward, and extremely bad reward would be something like burning the food or setting the kitchen on fire. So the rewards can be positive for good things, negative often for bad things. Now, compared to supervised learning, it's actually a much harder problem. And the reason it's harder is because of credit assignment. What does that mean? In reinforcement learning, the robot does not get told as it's acting what was right or what was wrong. It's more like at the end of the day, or at the end of a lot of actions, it gets told this is a good outcome or a bad outcome. So the robot gets scored on outcomes, not on individual actions it's taking. And so when it sees something, does something, it doesn't get supervision of what mapping it should have from what it sees to what it's supposed to do, just gets supervised on outcomes. Now imagine you're a robot and you take a half hour to cook a meal and you get a 4-star rating. And you take another half hour, cook another meal, get a 3-star rating. Now, credit assignment is the notion of teasing apart what was different between those two cooking sessions that might have resulted in one being a 3-star, the other one 4-star. But it's hard, because it might be that you can't easily directly compare. You might have done some things better in the 3-star, actually, just some other things worse that made it overall worse. And that is really the challenge in credit assignment, teasing that all apart. You can imagine you need more than 2 runs to tease that apart. That's why reinforcement learning needs a lot of trials before it's able to see what exactly is contributing to positive reward versus maybe negative. Stability is a challenge that in reinforcement learning, well, you're in a feedback loop. And so if you make a mistake, even just a small mistake, often you put yourself in a more difficult position for the next time step. If you put yourself in a more difficult position, you're more likely to make a mistake again, and this might spiral out of control, destabilize the system. Exploration is this notion that, well, in reinforcement learning, you're not told how to do something, you're just told whether an outcome is good or bad. So how are you going to find out how to do it? You have to explore, you have to try things. And, well, trying things you've never done before is key to learning, but it's also tricky, because how do you know what to try? There's so many things to try, and what's useful to try, what's not useful to try, that's a very hard problem. That's the exploration problem. So these are the 3 big challenges that make reinforcement learning very different from supervised learning. Now, in some situations, actually there's been a lot of progress. For example, in learning to play video games, initial result in 2013 from Vlad Nia and collaborators at DeepMind, it was shown that it's possible for a neural network to learn to play video games. And in fact, it was a single piece of code, and you could put it in front of one game, let's say Pong, learns to play Pong. Put it in front of Breakout, learns to play Breakout. Put it in front of yet another game, learns to play that other game, and so forth. And so it's a very general approach to master a wide range of skills. Then, of course, a little later, DeepMind showed it's possible not just to learn Atari games, but also learn to play the game of Go. For the longest time, people thought this would not be solved for maybe another many, many decades. But then all of a sudden, it was there. How come people thought it was far away and it immediately happened just a few years later? Well, essentially, traditionally, you would think of a game as I make a move, you make a move, I make a move, you make a move. A number of ways you can play the game of Go, if you count it out, is something like 10 to the power 280. Compare that to 10 to the 80-ish number of atoms in the known universe, it's a very large number of ways you can play this game. And so if you want to go through every possible way you might play and then guarantee a win by understanding every possible way you can play the game, you need a lot of compute. And it's quite understandable. People would guess that it takes at least another 100 years before we have the compute to run through all of that. But that's not how it was solved. It was solved by essentially doing pattern recognition, understanding that you can train a neural network as an image recognizer, white pixels, black pixels, empty pixels, and output a probability of winning for each side. Then you don't need to think through all the way at the end of the game. You just think one step ahead, which one of your moves gives you the highest win probability. And then you repeat. Of course, thinking one step ahead is not optimal because, well, this neural net is not super precise. And so if you still think multiple steps ahead and then only use the neural network, you'll actually get a better result. And that's, of course, what was done in solving this problem. But ultimately, the main reason this worked is because after thinking multiple steps ahead, a neural network was used that could fairly accurately evaluate the win probability of each side to help guide your moves. Then, stepping up in the video game world, OpenAI showed that it's possible to learn to play the game of Dota 2 one-on-one at the level of the best human players and 5-on-5 comparable to the best human teams. In the meantime, at Berkeley, we're showing that deep reinforcement learning allows to learn to control robots. And what you're watching here is actually learning in action. Initially, it doesn't know what to do, but over time, it gradually figures out how to run. Now, again, the beauty here is that you don't need to have anything specific to this robot. You can actually have a piece of code. In this case, it's trust region policy optimization with generalized advantage estimation. But a specific piece of code, you can run it on this robot, which has 2 legs, or you can then run it on a different robot that has 4 legs, and it'll learn to control the new robot that has 4 legs. You can, in fact, also put it in front of the video games. It'll learn to play those video games. And so it's a very general approach to solving problems where you just let the system figure it out on its own. Very different from how things used to be, where people would design dedicated algorithms for 2-legged robot control versus 4-legged robot control. Think about center of gravity, support triangles, dynamic stability, static stability. All of those things came into play to try to figure out in your head, what does it mean to design a controller for controlling a walking robot? But now it figures it out on its own. Here the task is to learn to get up. And so this robot's supposed to stand up, and over time, it's exploring right now. It's trying to get its head higher and higher, and ultimately, it's all the way up to standing head height. In fact, at this point, it's possible to do this for a very wide range of skills. And it doesn't have to be a humanoid character. You can do it with something like a lion, and the big red arrows are big perturbation forces, and you see it can sustainably run despite being pushed and shoved around. And you can do it with real robots. So here is Brett, Berkeley robot for the elimination of tedious tasks, putting the block onto that corner spot. Takes about an hour in real time to learn a vision system and a control system to put the block onto the target. This is a robot that we worked on with NASA. So this is called a tensegrity robot. It's a very special kind of robot. So the way it's set up is there is rods, the big like metal bars, and then there's cables, and the cables can be lengthened or shortened. And as you lengthen or shorten the cables, this robot will change shape. As it changes shape, the center of gravity will shift, and it might tumble over, and you can make it move. It's not very intuitive how to design a controller to do this, but again, with reinforcement learning, it's actually possible to learn a neural network policy that can reliably make this Super Bowl robot move off to the right in this case. You might wonder why a robot that looks like this. There's a couple of reasons. One reason is that volume in a rocket comes at a high premium. And so if you extend the cables, you can then actually compress this robot in a very small package. A bit like when you go camping, your tent, when you set it up, is large. When you put it all together in a little bag, it's very small. Same concept over here. Other thing is that it has some damping when it lands. There's a little spring to it. And another reason is that, well, if you think about if you want to get somewhere with a car, the size of your wheels might affect what you can get over. If you have a sphere, you have a wheel in every direction of maximum size relative to the size of your robot. So we saw a lot of examples where deep reinforcement learning could achieve mastery that is even better than human level on a wide range of problems. But the question you might ask actually is, how good is the learning? So you think about intelligence. It's one thing to master something. It's another thing to master it quickly. If you master things more quickly, it's a more intelligent system than one that takes a very long time to learn something new. So let's measure this. So in Josh Tenenbaum's lab at MIT, they had a bunch of people play some Atari games and check, how does the most sample efficient reinforcement learning method match up with humans. Turns out humans in 15 minutes tend to outperform double DQN after 115 hours. So massive gap in efficiency of learning. So how are we going to bridge this? Well, our starting observation is going to be that TRPO, DQN, A3C, and so forth, all the state-of-the-art RL algorithms are extremely general. You can apply them to any environment you can mathematically define. But environments we encounter in the real world are actually a tiny, tiny subset of environments you could, in principle, mathematically define. For example, in the real world, all environments satisfy our universe's physics. But if you mathematically define an environment, you could have it satisfy different laws. So the question then becomes, maybe that's where we can get our leverage. how can we have our algorithms become faster by taking advantage of the fact that in principle you have a strong prior over how the world works and exploit that when learning to solve a new task. Now, when you want to put in a prior, one way to do it is to say, well, I'm just going to put in a prior. I'm going to wire up the network differently, or I'm going to hard code something. Maybe that can work. That's probably pretty hard to do. The approach we followed is a very different one. We said essentially, well, let's look at the agent, interacting with the environment, and let's look under the hood at what's really going on. There's an algorithm and there's a policy. The policy is really what interacts with the environment, or it could be a Q function, either way. And then the algorithm updates the policy or the Q function. When it interacts with environment A, the policy specializes onto environment A. When it interacts with the environment B, the policy specializes onto environment B, and so forth. Traditional reinforcement learning research is all about modifying the algorithm to hopefully learn the policy more quickly. But after many, many years of such research, our algorithms are not nearly as good as human learning. So maybe rather than try to build our expertise into the algorithms, we should also learn the algorithm. Because maybe the algorithm can be learned from past experience, how it can learn quickly in new environments in the future. So we're going to make the whole agent learnable rather than just the policy or the Q function learnable. So what would it look like? You have an environment A, environment B, and so forth. Your meta-learning algorithm gets to interact with all those environments, and from that is supposed to generate a faster RL agent. And when this faster RL agent interacts with the world, it should learn very quickly. OK, so that's our goal. How do we formalize this? Well, one way to formalize is to say, well, what we really want is, again, an agent, which is parameterized. We're going to find the parameters for that agent such that, on expectation, when the agent is dropped in a sampled environment, then gets capital K trajectories or episodes in that sampled environment, we want it to be the case that the agent collects high reward. If we keep capital K small, for example, capital K equal 2, then it means the agent only gets to act for 2 episodes in each environment. If that's the case, then if it gets high reward under this objective, it means it learns very, very fast to adapt to a new environment. So now, how do we train this? Well, we set this up as our objective. We say we're going to directly try to find an agent that when randomly dropped in a training environment, within 2 episodes or small capital K episodes, gets high reward. And then we hope that later, when we go to a test environment, that the fact it can learn quickly in train environments means it can learn quickly in test environments also. So the generalization again here is not from training data to test data, it's from training environments to test environments. If you can learn quickly in training environments, the hope is that then consequentially you can learn quickly in test environments. So what do we make our agent of? Well, maybe a recurrent neural network. Why would that make sense? Well, it's a very generic computational architecture. So any computer program effectively can be represented if you have a large enough recurrent neural network. So that includes whatever computer program is representing a nice internal Bayesian inference on what the world could be like based on what's experienced so far, what's still left as possibilities, and so forth. In principle, that could live inside a large enough recurrent neural network. Different weights in the RNN means a different RL algorithm and a different prior are built into the network. When you get dropped in a new environment, the activations get reset, and so the activations, as they change again as you act in the new environment, that is encoding your experience. So the learning in the new environment is encoded in the activations of the RNN. The objective itself is actually a reinforcement learning objective. Standard reinforcement learning looks exactly like this, except that you always sample from the same environment. So when you sample an environment M, it'll always be the same one, always the same game, same robot, and so forth. Here we're going to always sample a different environment for a small number of episodes every time, and then to the next one. So how can we test this? One way to test this could be take a reinforcement learning problem where we know how to solve it and see if we can match up this learning to reinforcement learn with known solutions. So in general, RL problems are not that easy to solve. There's not that many where we have provably optimal solutions, but for bandits we do. So in a bandit problem, you get to choose at any given time which arm you want to pull. When you pull an arm, you might get a payoff or you might not get a payoff. Each arm has its own probability distribution over payoffs, but you don't know that distribution. And so you have to explore to figure out which ones are more likely to pay off, less likely to pay off, and then exploit. So the core of RL is in here. What's not in here is that the state of the world never changes. After you pull an arm, nothing changes. All these arms continue to have the same probabilities of payoff. And then you go again. So you always reset into the same state in an environment here. Simpler problem than general reinforcement learning. As a consequence, humans have come up with asymptotically optimal approaches. Gittins, Thompson, and so forth. So we could take our learning to reinforcement approach, put it in front of a bandit problem for, let's say, I don't know, 20 pulls. Then put it in front of another bandit problem for 20 pulls. Put it in front of another one for 20 pulls, and train it over time to hopefully become fast at adapting to whatever next bandit problem it's faced with. Then at test time, we'll give it a new bandit problem it's never seen before, meaning it doesn't know the underlying probabilities of payoff of each of the bandits, and hopefully it can quickly adapt to that new situation and get high reward. We did this for different numbers of bandits and number of pulls you can do for each bandit, compared with all the human-designed asymptotically optimal ones, and we see that RL squared is about as good as the human-designed asymptotically optimal one. That's the best one, which is Gittins. Now, this is a simple environment. We have optimal solutions already. How about other environments? Well, how about Majoko, half cheetah? Here, you could say my family of tasks is, it's always the same cheetah robot, so I'm not going to change that, but the reward function will change. The reward depends on the speed at which you're running, and sometimes you get rewarded for running at 0 speed, which is standing still, sometimes for speed 2 meters per second, 10 meters per second, and so forth. And fast adaptation here means that as the cheetah starts running in a new environment, starts moving around, it should quickly figure out how to maximize the reward that it's now getting. We see actually this approach in the first episode already can achieve pretty much maximal reward, because it has learned to quickly identify how to associate reward with speed and then start running at the appropriate speed. Same thing for ant, same problem, and again here in first episode, it's able to already adapt to whatever the task is at that time. How about some harder problems? Navigation. Imagine your robot is dropped in a building and it doesn't know what the building is like. We are looking at a map on the right, but the robot does not have access to the map. It just knows it's in a new building, gets first-person camera view. That's it. It sees into the building. It's supposed to find the red treasure. Could be behind a corner here. At this point, it should go straight ahead, but initially it doesn't know that, of course. But hopefully it would learn that going to the red treasure is a good idea. But beyond that, hopefully it would learn how to explore a new building even when it cannot see the red signal, and map out that building such that when it gets dropped a second time in the same building, it goes to the target quickly. So let's see what happens. If you just randomly explore a new building, here's what you get. You just kind of stumble into the wall and don't really go anywhere. If you have been in many, many other buildings before, you never had access to a map, but you always got dropped for 2 episodes into a new building. You're supposed to maximize reward, and then now get dropped into a new one. Let's see what the acquired behavior looks like. The agent has learned to run down hallways, to look around corners, and when it sees the red target, it runs to it. It knows it's dropped in the same one again, and it finds a short path to the target again. So this is actually a very hard problem. It's in robotics often called simultaneous localization and mapping, SLAM, because it has to build a map to remember how to go there again next time. But it's actually more than that. In SLAM, usually human will joystick the robot around, and then the hope is the robot builds a map. But here, the robot has to steer itself and localize and map all at the same time. How well does it work? Well, if you look at the learning curves, what's interesting about meta-learning is that when you look at it here, your first thought is probably, okay, the train is doing a lot better than the validation. But that's actually not what we're looking at here. What we're looking at here is, in meta-training, in something like this maze problem, at training time, we can generate a new maze every single time. We never need to repeat the same one. So even during training, you can't really overfit because it's always new what you encounter. So what you see here is actually a few random seeds where sometimes it acquired the skill of navigating new buildings and sometimes it did not. Why might it not acquire the skill and just kind of be stuck and not get much reward? Well, the reason that could happen is because imagine you get dropped and you're just wandering around and you're wandering around for a long time and don't see any reward. Or maybe at the very end you see a reward. But at the very end it's been so long, you don't know how to do the credit assignment and you can't learn anything from it. And so if you're unlucky in your exploration, meaning that you get the reward always very, very late, you might just not get much learning signal to propagate through a recurrent neural network and be able to learn. What can we do to alleviate it? Somehow find a way to get that signal to go further. So we looked at a different architecture. Instead of a recurrent neural network, we looked at something that combines self-attention with dilated convolutions. So now this neural net looks back at all past experience effectively. Through dilation, is able to look back very far and then can use attention to get more detail. When you do that, you can actually solve bigger bandit problems than we could before. And you can also solve bigger mazes than we could do before. Here's an example of such a bigger maze. The robot, again, does not have access to the map. It's just trying to exhaustively enumerate what might or might not be in this maze, so where the treasure might be, which is now in blue. It's pretty unlucky, but I mean, this is just pure luck in that sometimes you're lucky, the treasure is found right away, sometimes it's the last thing you try. We specifically picked a run where it's the last thing it tries because that way you can see that it doesn't waste time revisiting things it's seen before. So it remembers enough to not go investigating things more than once, finally finds a treasure. So if you want to dig deeper into this, there's actually quite a bit of work on meta-learning for RL. There's a list here, and the list keeps growing. Maybe not all 100 papers every day on arXiv are on this, but there's at least a couple of papers every month that add on to this list, trying to expand essentially the effectiveness of this. What are some of the missing pieces? Well, missing pieces are the environments we looked at are definitely the maze navigation is pretty complex, but overall not as complex as the real world, of course. So how can we expand the environments? And keeping in mind that we need to run experiments fast. And so if your environments are too different, goes back to the earlier question, environments are too different, you might not be able to generalize easily and might not be able to get this working. So some environments people have played with are Wisdom environments that I showed, DeepMind Lab, then Mojoko environments. Then OpenAI has a retro contest where there's a bunch of games and game levels that are related to each other. And then the hope is that if you can learn quickly to learn to play one game level or a bunch of game levels, you should be able to be faster at learning a new game level of the same game you've never seen before. And then recently, there's this release of Metaworld by Kevin Yu and collaborators looking at, in this case, 50 different robotic manipulation tasks in simulation. And the hope is that if you learn to learn on the first 45, let's say, then hopefully you can learn quickly on the last 5. Let's pause for questions again here.
All right. So if you're solving a new RL problem, which of the many algorithms that we've talked about, which one would you use as a baseline, or what would your starting point be?
Yeah, so let me give maybe a very concrete example. So this summer, we wanted to revisit if we could get a robot to organize laundry. Okay, so we did this at Berkeley about 10 years ago, but with a very hard-coded approach, which was a little bit brittle at times, and made it hard to expand upon from towels to other things and so forth. So we thought, well, what if we do reinforcement learning? Can we get it to work? Because if you do it with learning, maybe you can expand more easily to other tasks than if you hard code things. So first step we took was we took an algorithm. We said, okay, what might be a reasonable algorithm that we might want to use? I would say sometimes there is 3 leading candidates. If data collection is very, very fast, very cheap, then because the latest data is going to be most informative, you would typically run PPO. proximal policy optimization, which was used, for example, for Dota 2 and for the OpenAI Rubik's Cube and so forth. Now, if data collection is very expensive, then you don't want to always use your latest data to update some, because you want to actually reuse your old data many, many times to update your network many times based on any data point you collected. You have a replay buffer and so forth. That's where Q-learning lives. So DQN, Rainbow, things like that. And then there's a kind of somewhat interesting intermediate, which is soft actor critic, which still keeps track of a current best policy, unlike Q-learning, which is just Q functions that it keeps track of. Soft actor critic keeps track of the current best policy, but is nevertheless able to do some off-policy updates. And so I would say, depending on the problem, meaning depending on how easy or hard to collect data, it would be one of these three. Or in the extreme, if it's really hard to collect data, you'd go to a model-based approach, model-based RL approach, rather than model-free. Now, for our problem, we thought we're kind of at a happy intermediate where soft actor critic is a good fit. Then we said, OK, how are we going to do this? The easiest way to get something working in reinforcement learning is to make sure it always works. Because when it doesn't work, it's often very hard to find out what is wrong to make it work. So at any given time, you want it to be working. Imagine we asked the robot to organize some towels, and we ran reinforcement learning, probably wouldn't have worked, and would not have known what to change. So we said, OK, we need to make the problem simpler. So we said, OK, let's make it simpler. First, let's go to simulation. Then even in simulation, let's go to actually extending a rope instead of spreading out a towel. Actually, let's make it even simpler. Just go to moving a point mass onto a target. And so the way we set up the problem was we go from point mass in simulation to rope in simulation. Rope in simulation point mass could be from state, then from images, then rope from state, from images. For rope, you could say only actions available is the endpoints, or you could have actions that are anywhere on the rope or anywhere in the space. And so you have all these levels of difficulty. Then you go to towel. Again, initially, you could say the actions are only the four corners. Nothing else is available. Or then you could say anything on the towel, or then anything in the space. And so key really for success there was this notion that you pick a problem that you want to solve and simplify it down to something that you just say, it's for sure going to work. There's no way this doesn't work. Because that allows you to tune all your hyperparameters on that simple problem, learn as quickly as possible, make the problem slightly harder, do some retuning, but you get signal because it's succeeding. It's just succeeding slowly because the problem's slightly harder. You retune and repeat. And I think that's really key to success, is that you're always succeeding, retuning your hyperparameters till you get to the problem you really want to solve.
I'm going to synthesize a couple of questions here, but there have been a couple of people that are curious about real-world applications of reinforcement learning. And so, I guess the broad question is, where do you think reinforcement learning is going to be used in the real world? More specifically, if you can comment on healthcare. So there are apparently RL environments available for ICU and diabetes regulation. And then if you can also comment on, supposedly there was a claim made in the recent ICML RL workshop that contextual bandits just works better than RL for real-world applications. So people were curious what you think about that.
Yeah, good questions. So maybe let's first look at the distinction between bandits and RL. So bandits in some sense are a part of RL. They're the simplest version of reinforcement learning problem where there is no state in the system, or the assumption is that there is no state. You just assume that whenever you're asked to take an action, the environment you got dropped in does not depend on past actions you took. Now, in reality, that's never going to be 100% true, but you can maybe think it's close to true. So imagine, advertising. Somebody comes to a website, you have a profile for them, and you essentially assume that given this profile, I need to present an ad that hopefully makes them click, or otherwise makes me learn something about that type of person, what they're not likely to click on that I can leverage in the future. And then the assumption in Bandits is that after that happened, the next person comes to the website is completely independent, no relationship. And so the beauty of a Bandit formulation is that what you need to learn is much, much simpler. You don't need to learn to navigate the world, don't need to learn to make people change state. You just need to essentially learn a mapping from essentially a profile, let's say, of a person that you're presented with, or a profile, a situation you're presented with, to the best action available there. And of course, the pulling arms that might pay off is the canonical example. And so whenever you can apply that, that's a great thing to apply. Now, even within that, I would make two distinctions. Like one way you can run this is you can run it as, just to be clear, contextual bandits means that you actually do have information about who shows up, let's say, on your website, and you can condition on that for your action. Now, you could do this in a model-free or a model-based approach. Model-free would mean that you try to directly learn a policy that decides what you're going to present. Model-based would be the other way around. You would say, and normally model-based learns a dynamics model and a reward function, but in a bandit problem, model-based would mean just learn a reward function. You would learn the mapping from profile of who shows up and what you present to them to what they click on, let's say. And so that's the model-based approach. And if you do that, which I don't think many people do, in principle you could be more sample efficient, because now you can use your model to optimize actions you use in a new situation. So that's bandits, and whenever you can apply that, it seems the natural thing to do, because if the simple idea applies to your problem, you should definitely follow it. Now, let's say you have more complicated problems where there's a change of state. So let's say diabetes. A person has some internal regulation of their glucose levels, insulin levels, and now it's not that, at current time you make a decision and what happens next is independent of that. In fact, if you injected insulin, that'll affect glucose levels very directly. So you can't just assume you're faced with a situation that was not dependent on what you did before. You have long-term consequences of your actions. And so there, I think, what I've heard is that for the physical, for that specific example, it's not too hard anymore to build a simulator. So you can build a simulator for every specific person that can simulate the chemical processes involved in glucose and insulin interacting with each other. What is much harder is to go to the behavioral. So how do you encourage a person to do the right thing? So how do you encourage them to maybe, okay, you just had a meal, a short walk might be better than just sitting down another hour now. Or how do you encourage them to maybe eat something different? Things like that. And modeling people's reactions to that is much, much harder. And there's a chance that they just let go of their app. And they just say, hey, this was just really annoying. It asked me to do things that I really don't like to do. This is just frustrating me. I'm going to stop using it. And so there is a lot of subtleties there that are much harder at the behavioral level than at the physical level. In general, I think RL has a lot of applications whenever you have a great simulator of the environment, because you can just train for a long time in simulation, put it to work. And so the glucose regulation chemical thing would be an example there. If you have robotic systems where you can simulate well, be a good example. If you can get demonstrations of how to do things, you can pre-train your network and then do RL to fine-tune. So that's another example where you can apply it. But if you need to do RL from scratch in a place where it's expensive to collect data, it might be a stretch to try to apply it at all.
So it seems like there's a lot of successful examples of meta-learning in reinforcement learning and supervised learning on images, but NLP applications are relatively rare. I guess the first question is, do you agree with that? And then the second question is, if so, why do you think that is? And are there any approaches that you think are promising to make it work?
Mm-hmm. Let's get to that question later after I cover the unsupervised learning.
Sounds good. So in Rich Sutton's Bitter Lesson essay, he made a claim that general algorithms work better than human design solutions. But we as humans use heuristics that come from evolution, and we don't start from scratch. So do you think that the future breakthroughs will be more general search, or do you think there will be a swing back where we use more experience and knowledge for directing this search and solution space?
I think that's an open question, and different people will make different bets on what they think is more promising, and we'll see what happens. Personally, I think where a lot of the opportunities lie is in how to leverage a lot of past experience in RL to learn the next thing more quickly, essentially the few-shot learning or the meta-learning setting. And so in that sense, I think it starts coming down to essentially algorithms that can look at a lot of data from the past and somehow extract signal from all the data instead of maybe just from recent on-policy data. Comes down to setting up environments that are amenable to this. So a lot of the thinking has to go into what are the environments to even train in? Is there a natural progression or curriculum of environments to train in? And so you can actually, in some sense, start thinking about RL as, if I want to achieve very high level of intelligence of my system, and I have an algorithm already that can do RL, what is the best sequence of environments to embed this system into to get as close as possible? And so that's now a different kind of problem. So it's still a lot of human input in some sense, Because if you don't do any human input, you might have to like re-simulate all of evolution, and you might not have any control either over what the outcome is. But if you can kind of put the input at a slightly higher level, if I put the systems in this environment, what is the level of intelligence that comes out? If you can start getting intuition for that, I think that'll be very interesting. A good recent example was from OpenAI. It was the hide-and-seek environment, where a bunch of agents that were running around. Some were trying to hide, others trying to seek. And so these environments were designed with human intuition to allow them to get more intelligent behaviors over time as they compete with each other. And so that direction seems pretty important as an extra layer. That's not just about algorithm or hand design. It's actually thinking about in which environment do you need to learn to get intelligence to emerge.
All right, there are many more good questions here, but maybe this is a good point to move on to the next section.
Okay, yeah, let's look at imitation learning. So actually, especially in robotics, there's been a lot of success in imitation learning, but all these kind of canonical successes that people might have seen from the past, helicopter flight, legged locomotion, knot tying, putting dishes into a dish rack, predicting where taxis are going to go, well, they all follow the same paradigm. They follow a paradigm of collect many demonstrations. Your imitation learning algorithm then turns that into a policy that can interact with the environment. Now, let's say you need to assemble a chair. Well, you'll get a lot of demonstrations for assembling a chair. You need to assemble a table, get a lot of demonstrations for assembling a table. And every new task, a lot of new demonstrations. Wouldn't it be nice if we only needed one demonstration for a new task? So we get maybe still some demonstrations ahead of time, but then from that, we'll learn something that can one-shot imitate. So then once it's been learned, give it one demonstration of a new task F, it just knows what to do. Or one demonstration of a new task G, it knows what to do. So again, we're sometimes shifting the data burden to what happens ahead of time. We're not going to be able to escape what I'm going to present. It's not going to escape the need for a lot of demonstrations, but there's going to be a lot of demonstrations on other things ahead of time, such that in the future, for the new things, you need a very small number of demonstrations. How might we be able to formulate this? Well, here's one way to do this. Imagine your demonstrations you get ahead of time are such that you always get a pair of demonstrations. So for every task, you get 2 demonstrations. Then you should be able to learn something about the characteristics of that task, because those 2 belong to the same task, those 2 belong to the same task. And then when you get one demonstration for a new task, you should be able to predict what the others for that new task would look like. Make this even more concrete. What you can do is you could say, I have 2 demos. I'm going to learn a one-shot imitator. The one-shot imitator takes in demo 1 of task I, processes it, analyzes it, and then gets one snapshot of a situation in demo 2 of the same task and has to predict what's going to happen next. If it can do that by accessing demo 1, it means it's learned something about how to index into one demo to predict what has to happen when you need to do it yourself in a new situation for the same task. Now, of course, we have many, many tasks I, and then the hope is that ultimately something emerges that when we give it just demo 1, it knows how to do the first action for the new situation, for the new task. Then it sees the result of its first action, process, repeat, 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 completes the task. Here's a set of environments we could look at. Block stacking. So here, task could be make sure C is on top of D, B on top of C, A on top of B. Now, the way the robot learns this is by seeing a demo where at the end you get this A on B on C on D. If we train the network shown here on many, many such situations, meaning we have many, many blocks, and in every task, some subset of the blocks is used and is put into certain stack configuration, then when we give it one demo of a new stacking shown on the left here, it should be able to index into that one demo to succeed at doing the same thing over on the right. So it's a little dark, but over on the right, it's getting the same blocks stacked as are being stacked on the left. It's doing that just from that one demonstration, understanding what to do in the new situation on the right for this task. The highlights you see at the bottom are attention. So on the right, it's showing which blocks it's currently paying attention to, and on the left, it's showing which time slices in the demonstration it's currently paying attention to. So you'll see every now and then it pays attention to all time slices, then it realizes where it is, pays attention specifically to that time slice, and repeat. So that's one way to do it. You can actually do it another way, and I'm not really sure which is going to work better long term. It's just kind of presenting you two ideas. We can do Mammal again. How can we do this? Well, if we have two demonstrations, what's a standard way to do imitation learning? You have input, let's say image, action was taken, do supervised learning from image to action. Now, if you do supervised learning from image to action, you have a policy, hopefully, that can imitate the demonstration. But usually you need a lot of demonstrations. With Mammal, what we're going to do is we're going to say we have two demonstrations for each task, and we want it to be the case that we call one of the demonstrations training task, the other one validation, training data, the other one validation data. We can do just gradient updates on the training data, the one demonstration, and have a good loss on the validation demonstration. If that is true for a wide range of tasks where we have pairs of demonstrations, then it's likely the case when in the future we get one demonstration of a new task, we can just do gradient update based on the sequence of image and actions in that one demonstration, update our neural network, and get a policy that does well for the new task. So here's object placing from pixels. So input demo is done via teleoperation of the robot. So somebody is teleoperating the robot, steering it, looking actually at the same camera feed the robot is getting, and placing the apple into the blue bowl. The robot gets that one demonstration. Watch that demonstration. It's done a lot of training ahead of time. Now it watches this demonstration, does gradient update based on image and action pairs from this one demonstration. Now it's faced with the same task, namely it has to put the apple into the blue bowl, and the policy knows what to do. At training time, shown on the top left, it never saw that blue bowl, it never saw that red apple. It saw other objects being placed on top of each other, and also always saw it in a pair of demonstrations of the same task. It's always the object you're holding is going onto one of the objects on the table, and it internalized that concept, and now with one gradient update is able to internalize that from a new demonstration. Okay, but one thing that's a little unsatisfactory about this is that your robot actually has to be teleoperated. That's kind of tedious. It's nice when you can just show something with your own hands. When you show something with your own hands, the actions are not available, not in the format the robot needs them. So what can we still do? Well, there's actually a very general principle. In the Mammal setup, we have a training loss and a validation loss. For now, we've always assumed they're the same loss, image to action or image to category, something like that. But they don't have to be the same loss. We can make them different losses. And if we train with a different train loss and validation loss, essentially what we're saying is I want it to be the case that if I do a training update, a gradient update based on a training loss, the result is a new parameter vector that actually does better on the validation loss. And because we're optimizing this whole thing, the neural network should shape itself in a way, train itself in a way during meta training that gradient update on training loss is what helps you with validation loss. So we have different losses for validation and train. The validation loss will still be the loss from observation to action. That means that at meta training time, we still need teleoperated demonstrations. But the training loss will be from observation at the current time to observation at the next time. So just image prediction, next image prediction. That means we don't need to teleop. We can just do it with our own hands, and the task there is just predict the next image in the sequence of images during the demonstration. And the hope now is going to be that at meta testing time, when all we have is somebody demonstrating with their own hands, the video of that will define the loss, the training loss of next frame prediction. A gradient update against that training loss will lead to doing better on the validation loss, which is action prediction. So let's spell this out in a network architecture. Our network will now have two output branches. One for the validation loss, which has the actions as output. One for the training loss, which has the next frame prediction as output. Of course, they share a big part, and that's why an update based on the train loss could improve performance on the validation loss. Now, you could just hope for that to happen, but in Mammal, we train for that to happen. At training time, we ensure that updates along the train path lead to improvement along the validation path. Okay, so this is what we have. Now, let's say we directly try to predict the next frame. It's actually really hard to predict a full image. And in images, there's a lot of distractions. So maybe you're doing something with your hands here, but there's stuff happening in the background. So how do you make sure that it focuses on learning the things it needs to learn, that is the action, not other things? Well, this might sound familiar. Who here is familiar with generative adversarial networks? Quick raise of hands. Okay, most of you. So in generative adversarial networks, you say, I need to generate a realistic image. It's not about trying to generate an image exactly like the one in training data in terms of pixel values, but it's in terms of, does it look realistic? And another network will rate you on that. Well, what do we want here? We want to be rated in our image prediction based on how well it leads to improving our action prediction. So we'll bolt on another network here. That is a lot like the discriminator in GANs that gets to discriminate the predicted frame from the real frame in its own way. Not necessarily by doing pixel comparison. It can choose how it does that comparison, just like the discriminator in a GAN can choose how it discriminates between real and fake. What it will be optimized for through the Mammal loss is it'll try to find some discriminator that leads to backprogramming along the bottom path, resulting in good performance in the top path. Once we have this in place, this is what we can do. A lot of training happens ahead of time with both tally-op demos and just with your own hand demos in pairs. Then here's meta testing time, a human demo. The video is captured. The robot has captured that video. Now, against that trained loss, does next frame prediction gradient update. And then now we're going to watch along the validation loss branch where the actions come out, what it has learned from this one demonstration. And we see that it actually has learned to put, in this case, the peach onto the target bowl. Okay, let's maybe again pause for some questions.
Can you comment on sort of the idea of imitation learning generally and whether you think that has applications outside of robotics, like maybe for scheduling?
So yeah, I think the beauty of imitation learning is that wherever humans are doing something already, in principle, if you log that data, you could train a network to match up with that. So scheduling is a good example. Maybe you see humans doing scheduling based on preferences of a person, what they're willing to schedule in what kind of time slot, and then it can predict automatically what the next decision is going to be. Similarly, where I'm always hoping somebody will build something better is essentially if you work in Google Sheets or in Excel, often you find, at least I find myself tediously like filling out some things, but after I fill out the first thing, I feel like a human would already know the rest that I'm going to do for the next 5 minutes. And in principle, if you collect all the data from everybody working in all Google Sheets, it seems like it should be possible to understand what's likely to happen next. So I think in a lot of situations where humans are doing things and humans feel like some other person could already predict what they're going to do next, my sense is that a neural net should be trainable to do the same thing.
That's all the specific questions on imitation learning. So maybe we'll take the rest of them for a later section.
Sounds good. So next session is going to be on domain randomization. Actually, if you want to learn a lot more about domain randomization, Josh will give a lecture next week, which will go online a few weeks after probably. That's an hour and a half on this topic, and now we have about 10 minutes. So look out for that if you want to learn more after this. So motivation for simulation is that it's less expensive, faster and more scalable, less dangerous, easier to label than real-world data collection. But how can we make sure we learn something useful rather than something that only works in the simulator and not in the real world? Well, one way is you've just built realistic simulators. If you do that, then that's going to be taken care of. But actually getting high realism, high fidelity is very hard to do. A lot of specialized work has to happen, and even then, it's often not really matched up. And when it gets closer, often your simulation becomes more expensive again, because doing very realistic simulations, renderings, can be quite expensive too. So that's one path, and definitely should continue to be pushed. But what are other approaches we might be able to follow? Something called domain confusion, domain adaptation. What it does says, hey, what if I have two data sets? One from simulation, one from real world. I'm going to train one neural network, and it's going to be trained on any of the data. It needs to be able to do the right thing no matter what data you feed in. What if you set it up in a way that after a certain layer, you should not be able to know anymore whether the data came from sim or real? So you can put a discriminator there on the latent variables, the hidden variables, that the essentially neural net unit activations. Feed a discriminator out that tries to predict whether these activations come from processing a real image or a simulated image. If that discriminator is fooled, it doesn't know the difference, and anything that comes after those activations is going to be equally applicable to real world and simulation. Now, of course, now you have a discriminator and it fights against the signal you're trying to extract. It's not always easy to get to work, but it's a way to then have the second half of the network be trainable fully in simulation without any issues that it might not generalize. It's another approach that's actually seen a lot of success, which actually the previous one here has another actually benefit. Imagine you were building a machine learning system and you have some requirements that you want satisfied. Like maybe you say, I don't want to have the prediction that comes out of it depend on gender. I mean, who saw all the Apple Card news last week? Well, there's a lot in the news, like married people, and like if you're the man or the woman, it actually affects, yeah. So now, I don't know what they did there, but I could imagine that they did not feed in the gender. It's totally possible they did not feed in the gender, but that the machine learning system still had a bias because maybe there were other variables, representative gender, somehow going in there and something happened. Who knows? In general, you could have some variable you don't want to depend on. Maybe it's zip code. Maybe it's gender. Maybe it's age. Maybe it's race. Maybe it's yet something else. But it might be that there are other variables in your input that can help you predict that variable you don't want to depend on. And so even when you erase that one variable, you still have the information actually available. So this same idea applies there. You can say, after a certain number of layers, my hidden activations, my activations of my neurons there, if I, from those activations, try to predict back out the variable I'm not allowed to depend on, if I can succeed, I have not erased the information. If I cannot succeed anymore, then that means I've successfully erased that information. So it's a way to essentially generally make sure certain information has been erased, not just by leaving out an input, because it might implicitly in other parts of the input. Now, to go from sim to real, one thing that's been extremely effective, and Josh has been one of the pioneers of this direction, is to actually do something that before we started working on it seemed like it could never work. Imagine you just train on the images on the left, none of them look realistic, and you want the neural network to still succeed on the image on the right at predicting, let's say, where the hexagonal block is. Say, well, those images are so different, such an unrealistic simulator, how is it going to learn enough from the unrealistic simulator to make a good decision in a real-world image? Well, the high-level intuition is that if you randomize your simulator enough, it might be always unrealistic, but it's unrealistic in so many different ways that maybe the only consistency across all of them is what's also in the real world going to be consistent. You might be able to learn in your neural network the thing that matters for the real world. And so you might randomize over textures, lighting conditions, occlusions, viewpoints. You randomize over all the things that you know don't matter. Even if none of your renderings are realistic, maybe you learn about the thing that does matter that you didn't randomize away, of course, and you can still succeed in the real world. Some evidence we saw from Sergey Levin's group was that they had a quadcopter learn to fly down hallways, trained in semi-realistic renderings, but no real-world experience, and then deployed in the real world and could navigate down hallways. Now we wanted to look at something more precise, predicting precisely where an object is in a scene, and make the renderings even less realistic and not pre-train on ImageNet anymore. So really no real-world data at all. Well, here's what happened. Horizontal axis, number of training samples, all from the simulator. So no real-world training samples. Horizontal axis is only samples from simulator. Vertical axis is error in real world. So we see the error in the real world gets driven down consistently as we get more simulated examples. It actually gets driven down to about 1.5 centimeter error, which is essentially the best you can hope for a very careful calibration for a monocular camera system looking at an object on tabletop. If you dig a little under the hood, what you'll see is, well, the number of unique textures really matters. So if you train the same amount of simulated scenes, but initially you limit yourself to only 10 textures being used when rendering the scene, then you go all the way to 10,000 textures, you actually do a lot better. So really critical. How about pre-training on ImageNet? Well, it helps. The blue curve is pre-trained on ImageNet. You start at a better spot, but actually after about 8,000 examples, you have caught up purely training in simulation. Now that's just finding something. How about picking objects up? Well, so if you wanted to learn that in simulation, you need a lot of meshes of real objects put into your simulator. But how are you going to get those? Well, there's something called ShapeNet, has a few tens of thousands of objects, but that's not enough to fully learn this. So what else can you do? You can actually take these objects for which we have meshes, slice them up, and randomly recombine them. Now you have objects that locally are like real objects, but globally are not like real objects. We can generate as many as you want. Train on that. Actually, you can see I'll skip the numbers here. Let's look at the demo. You can see it actually learns to pick up objects in real world without any real-world training data. Now, by no means is grasping a fully solved problem, but this result shows that you can do surprisingly well when training just in simulation and then faced with real-world objects, and it knows how to pick them up for a good fraction of them. Now, should take us even to a whole other level. You can train fully in simulation for a full robot hand. No training in the real world. Just in simulation, learn to reorient. Now you're going to need a little extra here. You can't just learn across many, many simulators and hope it's going to work in the real world. Because it's just very complex, and if you try to make your simulators too close to each other, it's not going to work in the real world. If you make them too different, there's not going to be a single policy that succeeds in all of them. What you can do, you can go back to the few-shot reinforcement learning. You can learn to adapt quickly to the simulator you're in. So the idea we covered early on in this session, learn to reinforcement learn against many, many, many simulators, such that when you're faced with the real world, it turns out you can adapt very quickly also to the real world. So here is that in action. There's some work from OpenAI showing that it can now, in the real world where it's never been trained, reorient the block to match the orientation at the bottom right. This is from about a year ago. Then this result was extended recently to show you can even do it for Rubik's Cube manipulation. So what you see here is a Rubik's Cube being solved by the robot hand, even though it's never been trained in the real world to solve this Rubik's Cube. It's only been trained in simulation, but it's been trained across so many different simulators, different friction properties, different geometries of the hand, different dynamics of how the tendons work and so forth. You randomize over all the things that you're not so sure about how it's going to work. And then at some point, it acquires the adaptive strategy, something that has learned to learn quickly and can adapt in the real world to do well. This takes a couple minutes, so I'm going to fast forward this a little bit. But we are watching this in real time, and we see it actually solve this Rubik's Cube. Just to be fair, the paper clarifies this doesn't succeed every time, and it doesn't always succeed at solving the Rubik's Cube. Sometimes it drops it. But I'd say the real research part here is that it's sometimes incredible. I mean, if you had asked somebody 5 years ago, is it possible to train fully in simulation and get a robot hand to do something in the real world that's this complex? They probably said, well, that seems unlikely because simulation is never going to match the real world for something like this. But this shows it never needs to match. Machine learning can make up for it. You can learn to adapt to any type of simulator, and thanks to that, also learn to adapt to the real world very quickly. And here it is, fully solved. All right, let's take another quick pause here.
Yeah, I think the specific questions on domain randomization already got answered. So maybe my suggestion is, like, let's move on, and then there's a bunch of general questions that we'll pull in at the end.
Okay. Actually, what I'm going to do is I'm going to skip over architecture search, because I think we have about 15 minutes left, and there's a couple of other things I want to cover. So architecture search, we'll go super quick. Architecture search is the idea that right now, data plus computation plus ML expertise, replace it with just data plus computation. The idea being that if you look at progress in computer vision, it's about new architectures. It's humans searching over new architectures. Why not just have some search algorithm in the computer search over architectures? Try many different architectures, see which one works better. This many filters, that many filters, this tried, that's tried, all those things, just search over it. Exhaustively searching might be too expensive, but maybe you can run reinforcement learning. Essentially, the idea here that Google thought was you have a controller neural network, an RNN, that outputs a specification of the network, just like you would specify it. Layer 1, this many filters, this is the width, this is the height, this is the depth of the filters, this is the stride. Do we do pooling, not pooling, what kind of pooling, and do we have nonlinearities, and so forth, and repeat. Do we have a skip connection? All those things, make that all part of the action space of the neural net, and see if we can reinforcement learn a policy that will output good neural network architectures. So I'll go pretty fast here. I mean, we'll share the slides, but it was shown that you can get better architectures for visual recognition, a little better, and actually quite a bit better for some of the language problems. Instead of LSTM architecture, slightly different architecture that can do better on language benchmarks. You can also find smaller architectures, match the performance of the bigger ones, because you might say, well, one axis of performance is accuracy, another one is size of the network, which might tie directly into the amount of power you consume as you run the network. So key idea is that architecture is a string. You get an RNN trained with reinforcement learning to output good strings that are good architectures for your network, and do the same thing actually for your nonlinear activation functions. Another idea related to this is that, we did data processing, machine learning. How about really putting more emphasis on the data processing, data augmentation? You have one image trained into 7 images. Now you have 7 labeled images instead of 1. You spend a lot of time on designing that by hand. Can you just do it automatically? So Google showed you can actually have a policy, neural network policy, output the right data augmentation scheme for your data set to maximize performance and get better performance than you can get. So they say, let's use the same architecture, that state-of-the-art architecture, only change the data augmentation schemes, change nothing but the data augmentation scheme, and show that you actually get better performance by having better data augmentation automatically found by the neural net. It was a little expensive to run. Here are some references. At Berkeley, then we showed that with 1,000 times less compute, you can achieve the same. What's the main difference? The Google approach is to train a policy that output at the end of training was ready to output the data augmentation for each data point you feed in as you train again. The Berkeley scheme essentially says, let's just do population-based training. While you're training, you have a bunch of data augmentation, distribution over your data augmentation outputs, and you gradually, essentially, shift the policies. You have, let's say, 30 policies in parallel. You shift them as you're training, remove policies that are not very successful, replace them with policies that are more successful, and keep going. And then you end up with a time-varying population of policies. And you just do one run to find that time-varying population of policies, rather than doing reinforcement learning with many, many rollouts to help me find out one policy in the Google approach. Same results, 1,000 times less compute. All right, so how about unsupervised learning? So the rationale for unsupervised learning tends to be that we can use maybe unlabeled data instead of labeled data, because labeled data are expensive. But, well, how do we do it? We might learn a network that embeds the data, or we might learn weights in a network by training on the unsupervised task, or a kind of self-supervised task that is an auxiliary loss, and then have the main output perform better thanks to the auxiliary loss in the network. So the main families of models are VAEs, GANs, exact likelihood models, and these kind of puzzle things where you say, if I leave out a patch, can I predict it back in? Or if I shuffle things around, can I figure out how to reshuffle in the original configuration? If we look at progress in this space, the first results look like this. So this is a 10 by 10 grid of images generated. So unsupervised learning generated images by, again, when it's not been trained yet, then as you train, it becomes better at generating realistic images. At some point, it becomes somewhat realistic. This is 2016. At the time, it was also possible to do it with faces and have a structure. You go left to right. You change just one variable in your latent space. You get a different view on the face. That means that latent variable has a certain meaning. And then the hope is that when you later do supervised learning, because you have that meaning already available, you might be able to learn from less data. These were images generated in 2016. Of course, since then, it's become extremely realistic. If you go to this website, thispersondoesnotexist.com, you'll see images like this being generated. Anytime you refresh, you get new faces, and they all look extremely realistic, even though they're not real people. So at this point, realistic faces can be generated automatically, which is pretty crazy. Now, going back to the premise we had, can we do unsupervised learning first and then learn more effectively with supervised learning from less data? Well, for the longest time, I would say that wasn't very true, but this past year, this has really started to happen in image recognition. So here's a graph from a paper that came out in May. The red curve is if you do just supervised learning. Horizontal axis, number of labeled images per class, this ImageNet training. Vertical axis is top 5 accuracy. Higher is better. In red is fully supervised. In blue is you get to do unsupervised learning on the other images that you don't have labels for yet. What you see here is that actually by doing unsupervised learning, you can do a lot better, especially in the small data regime, than if you don't have unsupervised learning. And very consistently, it stays above till we're in the high data regime. So this specific one was done with contrastive predictive coding. Contrastive predictive coding, if you look at the results, then actually outperforms all the previous methods that were trying to do this by a pretty good margin, showing that it's possible to, in this case, this specific evaluation, you do CPC followed by just training a linear classifier, and it outperforms any previous system that had to pre-train to learn features and just a linear classifier on top of the features, because that's a way to measure that your features are actually informative about what you care about. Only get to do linear after means you learn some good features. What CPC actually looks like under the hood is you essentially break up your image into pieces, and you will remove a piece and ask it to fill it back in. But filling it back in is hard, because pixel losses are difficult to work with. So instead of just saying you need to fill it back in, you'll say, here are the 1,000 options. Which one of these 1,000 is actually the one that would be the best choice to fit in there? So it learns to discriminate between 1,000 options, or it could be higher or lower, but that's a ballpark, which one is the correct one. And so that's the loss being trained against that has gotten the best performance on these kind of systems. You can do this for images, you can do it for text. In text, you just train for the next letter prediction, next word prediction. Here's some automatically generated text from 2 years ago. It's trained on Amazon reviews and generates a new thing that looks like a review. Then, of course, was OpenAI's GPT-2, which got a lot of headlines. Was trained on a lot of Reddit data, I believe. And then after it's been trained on that, you give it a new prompt. And then you say, OK, what should I say next? Well, here's what it says next. It says more details about the incident. Then it gets a quote from a high-ranking official, U.S. Energy Secretary, say they'll won't let this happen again, and so forth. When you read this, it actually reads like something that could be real, but it's not. It's just made up. In fact, some of the text generated was so realistic that OpenAI decided that they should not make this tool available yet to the rest of the world, and do some kind of gradual release process where first release a crippled smaller network, see what people do with that, see if any countermeasures are needed, and repeat gradual build up to the full size network. Now, what do we want? Maybe you want to generate text that's good for email completion, but often the motivation for unsupervised learning is not generating new things, it's actually being more efficient on the supervised task you ultimately care about. For example, sentiment classification. Is this a positive or a negative review? It turns out from just a very small number of examples, it was possible to learn a sentiment classifier on reviews after the neural net had been trained on next character prediction. In this particular case, it's very positive on the book, but then the movie, which the review is really about, is very negative. Some benchmarks people look at that are actually really tricky. Winograd schema challenge. The trophy doesn't fit into the brown suitcase because it is too large. What is it? The correct answer is the trophy because it's too large to fit in the suitcase. What if you change one word? It is too small. One word is changed and now it realizes it should say suitcase. The suitcase is the thing that's too small. And so you really need to understand something about that sentence. You can't just say, what's the nearest noun? And I'm just going to grab the nearest noun and say that was it. No, you're not going to succeed. You need to understand the meaning of large and small and fitting to be able to do this. Another one is this one, the neural net got it wrong, but essentially modeling broader context. So there's another big challenge. Like if you need to incorporate a lot of context to come to an answer, the problem becomes a lot harder than when you just need one sentence to look at to come to an answer. What's very interesting in those problems is that the more in the data in the language problems, the more data you have access to. Horizontal axis is larger networks. You can train them on more data, the better you perform. So there's a very kind of direct relationship between training larger models and getting better performance on the final tasks, which is interesting because you don't get necessarily more data on the final task. You just get more general data. You can train your larger model on that data and then do better on the final task where you get a small amount of data. That's really, I would say that's essentially what people were hoping for when many years ago they started hoping that unsupervised learning would really help. I would say this kind of graph is exactly the kind of thing you're hoping for. All right, so those were some research highlights. What do we have left? Overall research team, research real-world gap, and how to keep up. And we have about 5 minutes left. So what I'm going to do each of those in 1 minute, and then we do some questions. So if we look at the overall theme, I think the overall theme in research is that, zoomed out, is that people use ever more compute to get big results. What might that mean for your research agenda? Well, let's think about the types of problems you might want to solve and what's involved. Data, compute, and human ingenuity. Now, you can categorize problems into two territories. One where it's all human ingenuity, a little bit of data and compute. Another one where it's mostly data and compute. Where would you want to be? Now, you might say, well, maybe if you're extremely smart, you want to be on the left, because on the left, it seems like there's more reliance on that. And on the right, there's not as much reliance on how smart you are, so maybe it's not the place to be. But I would argue no matter how smart you are, you want to be on the right. The reason you want to be on the right, where a lot of what you do depends on data and compute that's available today, was not available any time before, it means you're trying to solve problems nobody could even have tried to solve last year. And now you're not competing with the whole history of humanity trying to solve that problem. You're just competing with whoever else is trying today. Because nobody else could have tried it before. There was not the amount of compute, the amount of data to even give it a shot. And so a lot more low-hanging fruit on the right than on the left, because on the left, again, you're competing with so many past efforts. On the right, you are not. And so learning to learn, of course, falls very much into that category of you're trying to learn everything from a lot of data that was just never possible before. Then I want to highlight the gap between research and real world, especially for physical systems. Research is all about 0 to 1. If you achieve 70% on a benchmark, you say, oh my God, this benchmark's so old, so dated, I need a new benchmark. And it makes sense from a research point of view, because you're trying to do something that's never been done before, get a sign of life that shows that maybe this direction could be promising. For a real world point of view, especially for physical systems, where failure can be costly, 90% is not going to be enough. You need a lot more. And if you do the math, for example, for a robotic system, let's say you have a station in a factory or warehouse, and you have it complete 500 to 2,000 operations per hour. Well, imagine 90% success rate. 500 per hour, 50 failures per hour that you need to fix up. 200 per hour means 200 failures per hour that you need to fix up. Fixing is more time-consuming than doing. So fixing 200 things is probably way more work than just doing the 2,000, and so it's not very useful. Realistically, you want maybe 1 or 2 failures at most per hour. So that means if you do the calculus, well, for a 500 per hour station, you need maximum of 2 interventions means 99.6% success rate. 2,000 operations per hour station, you need 99.9% success rate. And so these are numbers people don't really strive for in research. In research, people move on long before they get there. And again, it makes sense. Research objectives are different. It's not that it's the wrong thing to do in research. It's just showing that there's a whole different set of problems you need to solve for real-world physical deployments that are not at all an issue in the way we do research today. So a lot of interesting challenges there that are, I would say, ahead of us. And I would say this is why we're not seeing many robots helping us out, because the robots are not hitting those success rates that we need to help more than they cause fix-up work. So if we make this more concrete, I would say actually for drones, it's probably the easier problem. Why? Because you're always up in the air. There's nothing else there. And I'm not saying drones inside a building, that's going to be hard again, but drones that are just delivering things over longer distances are in the outside world, it's always air. Driving is harder because now you're among other cars, you're among people, much harder to make those decisions, and also the cost of failure is really, really high because you could kill somebody. Now, manipulation, I would say, is kind of the sweet spot. I'd say drones is probably mostly held back from a technology point of view by regulation, actually, more than technology. Driving is held back by you need so much reliability before you can be considered okay to go on the road. Manipulation, in principle, is harder than driving because you're interacting with things rather than avoiding them. And so interaction is yet an additional dimension, but you don't need the same number of nines that you need in driving to be able to create value. And so in my mind, manipulation sits in that sweet spot where there's a lot of R&D still to happen, yet we should be able to get there relatively soon without the potential pitfalls of driving where it's really hard to get the reliabilities that are needed. So how do we keep up with all this? You should, at some point, read papers, of course. How you read a paper, we have a little guideline on this, but it's not reading them word by word from start to finish. You should actually do this in a more structured way, and I'll let you read that offline. What papers to read? You can't read all of them. There's too many. Here are a few pointers. It's a newsletter by Jack Clark from OpenAI. He used to work at Bloomberg. Highlights the last week of main things he thinks that happened in AI. And so it's a nice way to get a couple of papers per week that you might want to read. Archive Sanity is a recommendation system for reading papers. So you just go there and it starts recommending things for you or recommending things that other people have read as maybe relevant to you and so forth. And it feeds directly into archives. So it just takes the latest papers from archive and feeds them all into the recommendations you get. Twitter, people post about papers. There's a Facebook group where people discuss things quite a bit. And there's an ML subreddit with, a bunch of discussions too. The one big recommendation I have for reading papers is that form a reading group. Why should you form a reading group? Because reading papers is very time consuming. You need to find the right papers and then read them. Imagine you just have one other person in your reading group. You cut your work in half effectively. So you don't need a big reading group. It's actually quickly diminishing returns. But if you can just have one person reading with you, you can save half of your time and keep up with twice as much work as you could on your own. OK, that's it. Thank you.
All right, maybe we'll just do a couple of questions. So one of the examples that you used was, I think when you were talking about in the Meta-RL section, you talked about replacing LSTM with temporal convolutions, and that helped learn over longer horizons, right? So that's an example of taking an insight from one research field and applying it to another. And so the question is, how common is it that that type of thing happens, where you have a development in one area of research and then it gets applied in another?
Yeah, so I'd say it's very common in the architecture space, so neural net architectures. The transformer architecture, which is very popular these days, was developed with machine translation in mind. That was the application. People thinking, OK, for machine translation, we need to be able to keep around multiple hypotheses of what each word might mean. So we need multiple heads of attention onto the other parts of the sentence and the parts of the paragraph and so forth to tease out what this current word might mean in this context. That's where it came from. But then from there, it's essentially been used pretty much in every domain, something that always gets tried and then might often do better, actually very often does better than previous architectures. So I think in the architecture space happens a lot. Same with dilated convolutions. Same with the original attention. Happens a little less, I would say, at the algorithmic level, where things tend to be quite different. Let's say reinforcement learning, very different from supervised learning. But there's still some crossover. If you look at PPO, a very popular RL method, the optimization used is still Adam RMS prop. So people will essentially say, I have an RL problem I try to solve. I set up an objective, which I call a surrogate loss, run Adam or RMS prop, which is really coming from supervised learning, run it on that reinforcement learning surrogate loss, a few iterations, then come up with a new reinforcement learning surrogate loss and repeat. So I think at the level of algorithms and architectures, there's quite a bit of transfer.
This is a question that we postponed from earlier. So successful meta-learning, in computer vision and RL is pretty common these days, but in NLP it still seems rare. So can you comment on what the path forward there might look like?
Yeah, that's a good question. So I feel like in NLP, in some sense, people have found such a good unsupervised learning task, and that might be why the meta-learning is a little less common, because it becomes very hard to beat this unsupervised learning pre-training baseline, which is already doing so well and essentially serving the same purpose, right? Because what's the point of meta-learning? Meta-learning is you learn on other things in the past to then learn more quickly in the future. And in the RL meta-learning and in the classification meta-learning we saw, essentially learn on other supervised or RL tasks in the past and then learn more quickly in the future. But in NLP, people have been able to learn ahead of time on unsupervised data, which is the most convenient way to learn ahead of time, and then fine-tune well on the tasks later. So I think the bar is just really high to find traction with something that's more explicit meta-learning.
And then maybe the last question. There was a question about Bayesian deep learning. And so, it's a sort of high-level question. What's your opinion about Bayesian deep learning? Where is that now in 2019? And sort of what directions are you excited about there?
Yeah, so I would say you can distinguish two parts of Bayesian deep learning. One part is kind of the methodology, and the other part is how you use it, right? The methodology, probably still a lot of progress to be made, in that the things people use today are probably relatively simple compared to what it might be 5 years from now, because being Bayesian is, if you want to do it really precisely, is a very complex thing to achieve. The things people use today are already fairly capable. What are the main things people use? They use a variational approximation to essentially have, instead of a weight for each connection, you have a Gaussian with a mean and a variance, maybe just so the variance is really the new thing. Now, instead of just having a weight, you also have a variance on that. And now when you forward propagate in a network, you can sample for each weight from that Gaussian distribution and get a distribution as a consequence of outputs decisions. That's one way. Another way is to train an ensemble of networks. You initialize them differently, and because they're initialized differently, if they're large enough, only where the training data gives enough signal will they agree. Where there's not a lot of training data to support a decision, the ensemble will disagree. And so those are two different approaches to be somewhat Bayesian or approximately Bayesian that are actually used in many places. One, you understand when you don't know. It's not perfect. It's not perfectly calibrated. We have a notion of this input I have no support on in my training data because the different networks or the different instantiation of the weights give very different answers. Same thing in reinforcement learning can be used for exploration. You can say, well, this is something I'm very uncertain about. I need to go explore. And so quantifying uncertainty is a really important use for these Bayesian approaches. And I see it being used. I do see a lot of opportunity to make it better than what we have now, ensembles and just the kind of variational approximations that we have.
Great. I think that's all we have time for. Thanks again, Pieter.
Thank you.